So let's welcome Aaron to preach to us about programmable forewarning plane. Stage is yours.
Thank you very much. I am Aaron A. Glenn. Thank you for joining. If we know each other socially, I'm honored to be your drinking time background noise. Despite what you may have read on the summation there, this isn't going to be a talk on YAML. That was an offhand IRC remark that got promoted to talk abstract, which did get me down the path of rethinking this talk almost entirely. Originally, this talk was intended for NetNod in the corporeal times, in the before times when we could meet each other. So I'm happy to workshop some new discussion points in a hopefully friendly, certainly informal venue such as this. Previous talks of mine were focused on the what, why, and how. I'm going to try to switch it up a little bit and work backwards. The how, the what, and then go to the why. As an industry, we're comfortable with code even if we don't identify as a programmer, right? So hopefully I'm not going to scare anyone off who doesn't consider themselves a software engineer or a software developer. I'm hoping this is applicable and understandable and appreciated by operators, just plain old operators. I also want to begin with two assumptions that kind of underpin the rest of our discussion. I want to keep these ideas front of mind. Hopefully we can all agree that a packet network is a distributed system itself. So not just the applications that run on top of a network being a distributed system, but the network itself is a distributed system. And the other part I want you to keep in mind are the interfaces we've generally had, be it an operator or even a software developer. The interfaces we've been given to this distributed system have been almost universally atrocious, if not borderline criminal. So let's talk a little bit about interfaces. I'd like to start with one that's probably not as well appreciated as it probably should be. The ASIC SDK, Software Development Kit. Now, a quick recap of the vendor space here when we talk about Ethernet switching specifically. We have merchant silicon and we have vendor silicon. Now, even when we have vendor silicon, they still use merchant silicon. And when they use merchant silicon, they inevitably use Broadcom. Of course, there are quite a few others, Marvell, Mellanox, Innovium, Excite, Centec, Nephos, but Broadcom is pretty much what you're going to find under the hood. And over the past 15 years, their SDKs for their various chips and their various lines are practically legendary, not necessarily in a good way. If you'd like to know more about ASICs and more about merchant silicon, my friend Tom Strix has a great Cloudflare blog called ASICs at the Edge that goes into it quite well. It's difficult to use. It's obtuse, it's extensive, at times it's outright faulty. The Broadcom SDK is notorious for being extremely difficult to use. Now, I'm not just picking on Broadcom specifically. Even P4 Studio for the Intel Barefoot Tofino chips has its rough edges. Again, it's software, right? It's all software from top to bottom. Everything software can suffer from common software development problems. But the one I want to focus on is the one that's most popular. Merchant silicon SDKs that aren't open and proprietary. And in this case, the Broadcom one is pretty easy to point to. Now we have two interfaces here, right? We have our control plane that run our protocols, our management plane. That interfaces with some kind of operating system. And inside that operating system, we will find that software development kit. Now, whether that shows up as an abstraction layer or something different, it doesn't really matter. Ultimately, there's some kind of driver that goes down and interfaces with the actual hardware forwarding the stuff. That's the ASIC. Now, what we end up having is thinking sand versus us, the sacks of water. We're fighting with this interface that is extremely difficult to get tractable, to understand. Oh, damn it. I thought I had another slide here. Okay. What happens with this is this has a profound impact on what eventually happens upstack, the environment or the user experience of both the network operating system vendor, the people programming these things, and ultimately us, the network operator, the end user, the client, the interfaces that we have to these things. If the SDK or the interface to the underlying hardware is extremely difficult or impossible to track, then we're going to end up with a really, really bad time higher up the stack. And so ultimately, this is what I want to preach, as Max said in the intro here. I would like to preach that having a description and understanding the interface to the underlying hardware is paramount to having a more functional and a more easy to use network overall. If it stinks at the bottom, it's going to stink at the top. And what I really want to say is everybody wins. If we have a codified behavioral description, if our network switching infrastructure is actually described by code, everybody in the stack wins, right? Everyone talks about disaggregated networking. I get my hardware from one person, I'll get my NOS from another, maybe I'll throw in my own BGPD, Go BGP, BO routing, that new thing in Rust from Flock Networks, mix and match. If you're, proficient enough to do that. But even if you're not that person, even if you're just a systems integrator or a VAR, or even if you're just a CLI jockey, an operator that wants to get some streaming telemetry and configure a few knobs, everybody wins. Everybody wins by having their infrastructure, in this case, their switches or their Ethernet network function gear, defined and codified in code. All right, so how do we do that? Damn it. There we go. So how do we do that? As you may have guessed, we do that with P4. And if you haven't seen any of my previous talks or done any reading on P4, real quickly, the P4 stands for Programming Protocol Independent Packet Processors. And what I like to say is it really does do what it says on the tin. So again, not to be scaring off anyone who doesn't consider themselves a programmer. I, for the record, do not consider myself a programmer, but I'll use a little bit of programming language here. It's declarative. P4 is declarative. It says how the packets are to be handled, not what you do to handle them. It's high level. And I'll end this hopefully with talking about some higher level abstractions, but really P4 is a great intermediate representation, in my opinion. It's a good middle ground between higher level abstractions and ultimately software or hardware, Ethernet ASICs, vSwitches that actually do the work. Protocol independent. It doesn't have any concept of native protocols. That means it doesn't know what MPLS is. It doesn't know what Ethernet is. You get to tell it exactly what it is. If you want to come up with your own artisanal MPLS, if you have your own thoughts on IPv4, like our friend Elad, and you think IPv4 plus is the real hotness, well, you could do something like that. You could model that and write it in P4. It's variable length packets. All the P4 really does is mangle headers. It parses headers and mangles headers. So no ATM, no cells here, no fixed width stuff, right? What do I mean by processing a packet? Some of you might go, okay, yeah, a packet comes in an interface, some stuff mangles it, and then it goes out another interface. And some folks may have a greater appreciation having to fiddle with forwarding plane managers, ACLs, tables, TCAMs, FIBs, RIBs. RIBs are more of a control plane thing. FIBs, things like that. But what is actually happening? Let's abstract all of that away into some decomposable chunks, something that's a little more tractable. So here we have a very simple abstraction of a packet switch forwarding plane. And this one tracks pretty well with what's happening right now in most of your devices, right? A packet comes in, there's a fixed parser that chews up the headers. It already knows about MPLS, it already knows about Ethernet, it already knows about IP, even TCP, UDP in some cases. Chews those things up, then goes into a pipeline. And in that pipeline, using those headers and probably some metadata, it'll match against tables. It'll say, is this an Ethernet header? Oh, okay. Well, if it's an Ethernet header, does it have VLAN tags? Let's pop that VLAN tag off. What's underneath there? Is it MPLS? Is it IPv4? Is it IPv6? Then, ultimately, after a pipeline, it'll be buffered. Now, depending on the complexity, that may be the end of it. It gets deparsed and out it goes. Some of them may be a little more fancy and have an egress pipeline. I don't know why it's spelled ingress pipeline there. I just noticed that. Or you may have a secondary pipeline, or you may have a bunch more pipelines. Some Tofinos have 8 pipelines. The Tofino 2 does, I believe. Oh, I don't know if that's under NDA. Probably not. Anyway, if it is, I didn't say that. So you have multiple pipelines. Once you're done with all those match actions, once you're done mangling your packet, you put the packet back together, serialize it, put it out the wire, and out it goes. So hopefully with this model, we have a feeling for what our domain specificity looks like, right? Again, this is not a general language. This is domain specific for messing with packets, more accurately, messing with packet headers. So now that we've got a feel for the domain, let's take a look at what a P4 program would look like. Now, it's not that much different from any other program, probably a little more advanced than your bash shell scripts, but I've seen some advanced ones, and a little less verbose than your Java mess. So we start off with some libraries. We start off with some declarations. Then we describe what we want to parse, what we're interested in. Then we describe our pipeline, our match action tables, the ingress, the table, the match types, how to apply it, what to do. And then here in this case, we'll assemble that modified packet, and that's that. Now here we show a main. That's, if you're familiar with C or C++ programming, that's kind of the traditional entry point to the program. And here we'll see, it says here V1 switch. We have our parser, we have our different stages, our different packages, blocks of our pipeline defined here. We're not just protocol independent with P4. It's one thing to program a way to mangle packets, but we have to somehow represent what's actually doing the processing. And P4 strives to be both protocol and target independent. So when I say target, I'm saying the ASIC, the vSwitch, the FPGA, the SmartNIC, the DPU. We have to be able to represent what those targets are able to do, and we do that in the same language, in P4. Some of you might be following along and going, yeah, all of these processing, all these pipelines are different, and they have a very real difference. How would we model that? How would we be able to express something that may not even be programmable itself? Let's go back, or let's rewind back a bit to the environment of a P4 program, or the P4 environment, I should say. It consists of a P4 program, an architectural model, a compiler that then outputs artifacts that go onto a data plane, or the actual target, okay? This is, as they say, where the magic happens. If you have pretty good eyesight, you may have noticed in those includes a thing called v1model.p4. Now, this is an architecture that P4 program was written against. There are a few architecture models. One of them is a standard of the P4 Association. It's called the portable switch architecture. It's a little more involved than the V1 model. The V1 model is kind of the original simple model that came from the origins of P4. So let's take a really quick look at an example switch, an example architecture that's included in the P416 standard itself. I do implore everyone, if they have any interest in P4, to take a look at the specification. It's quite well written in very easy to digest prose. It's not too technical, and if you have an appreciation for any kind of network functions or packet processing, it's quite tractable and quite understandable. Now this one here, the P416 very simple switch model, includes all of the important parts of a P4 architectural model. So let's go through this example real quick. The very simple switch receives packets through one of 8 ports, which we'll see defined in the model shortly after this image. Now, through a recirculation channel or a port connected to the CPU is one of the outputs. So there's 8 in, 8 out, a recirculate you see here, or from the CPU and to the CPU. The very simple switch model has one parser, one pipeline, and one deparser. You'll see here in the white boxes, those are the programmable parts. The green arrows are metadata that's carried along after parsing during the match action pipeline part and on through deparsing until it's sent out and queued. So at the end of this, we have 3 ultimate places that a processed packet can go. It can go out one of the 8 Ethernet interfaces, it can go to the CPU, which is the control plane, or it can take a very special port and recirculate right back to where it started. Hopefully you have an understanding of this simple model from this image. Now let's look at what the P4 code describing it would look like. We'll start at the very beginning here. We include a core library. Every P416 every P416 program includes core.p4. It includes two definitions, packet in and packet out. There's not much else in there, so not much else to explain there. Here we have our port ID of 4 bits, or of 4 bits representing 8 different ports. Then we have a struct for in control. We have an ID for our 2 special ports, our recirculation port and our CPU port. Then we have another struct that shows our out control. Then some more constants, again outlining special ports. Then we go to the blocks. We have prototypes for each of the programmable blocks here. We have a parser that has a packet in and outputs parsed headers. Then we have a single control pipe that takes headers in and out. It also takes in any parser errors. It takes in the input struct and outputs the output struct. Then the last part we have is the parser. All of this comes together in a package called the very simple switch. Now, a lot of the questions that people ask are, well, there's a lot of stuff that we can't represent in P4, and one of them would be a checksum. These are represented with externs. If you're familiar with programming, this is more of like a foreign function interface, or FFI. Basically, what we tell in the architecture code, we say this is a unknowing black box. You can pass it this data, it will spit back this data. These are its methods, and that's that. It's defined somewhere else. If we go back to our model over here, on our data plane, we have externs and tables. We can fiddle them from the control plane, but ultimately they're provided by the vendor. It's not something that we can mess around with as an end user or an operator or the programmer. All right, so if we understand that very simple one, we can go and look at even more complicated ones. And I want to take a moment here to outline and make specific mention of a few open source models. The portable switch architecture is an actual standard that's actively being worked on by the P4 Association. I believe it's in its second revision, so it's in version 1.1. And it's kind of the architecture that everyone would like code to be written against. It's meant to be abstracted enough to reasonably model any of the Ethernet ASICs that you would find under the hood right now. Meaning, I could take the portable switch architecture and use that model to also model something like a Tomahawk 2 or a Trident 3 ASIC. One of the best models, unsurprisingly, that's open sourced is the Barefoot Network's OpenTofino model. And this is kind of what I'm, to use Max's phrase, preaching about. You take a look at the OpenTofino or the Tofino TNA.p4 architecture file, and it explains every single aspect of the Tofino chip, including the parts that aren't programmable, like the buffers and some of the queues. It also has some external cryptography functions to enhance things like MACsec or IPsec functions. All of these are codified, parsable, compilable in a P4 model. And when someone writes P4 against a Tofino, they're working against that model. So their P4 program would have the same structures and blocks that would match the Tofino model. Now there's even simpler ones. eBPF can't do much on its own. In fact, it's mostly a packet filter. It can decide to pass or drop. And if it passes, it can pass to XDP, which has a few hooks and can do a few things to manipulate them. Both eBPF and XDP are already open source modeled in P4, and those are used by their respective P4 compilers. You can take a look at both of them. All of these are on GitHub. You can take a look at them and get an even deeper appreciation for them. So let's talk about P4 targets today. You can have your infrastructure as code right now with a lot of the things that are already out there. Most of us are using some kind of vSwitch, some kind of software switch. A lot of us are using DBDK. Some of us are using VPP. And there are P4 targets that go for both of these. For DBDK, Intel just released one about 6 weeks ago now, maybe just a month ago. And it'll take P4 programs written against the portable switch architecture model and compile them down to DBDK bytecode. And I know I'm not using that right. I don't think it's called DBDK bytecode. The lowest level of the DBDK API. It transforms P4 directly into that against the portable switch architecture. So what that means, in the example that they give on there, you can compile a VXLAN implementation, and it comes out running as a DBDK module that you can load on your NIC. It parses, it works in both directions with any and all kinds of VXLAN frames. These DPUs, data processing units that everyone keeps talking about from multiple companies, Fungible, Pensado, NVIDIA BlueSpec, originally Mellanox, all of them support P4. Some of them, like Pensado and Fungible, as first-class citizens. Unfortunately, Pensado doesn't give you, under the hood, any access to the P4. They model they have 3 different models in P4 that they allow end users to use. Nonetheless, they're available to you, even if you can't program with them directly, and that gives you a solid interface to reason about what the behavior of the program, or what the behavior of the actual device is going to be, and how your program is going to behave on that target. Another one is Metronome. They're a SmartNIC company, if you're not familiar with them, and they have one of those many-core NICs, so 36, 72 cores, I don't recall exactly how many, but they also support P4, not quite natively. And of course, all of the FPGAs. Xilinx and Intel both have deep support for P4. They have their own proprietary models for that. The Intel compiler will actually let you use a few different models. Ooh, again, I don't know if that's under NDA. You can do more than just an FPGA model with the Intel one. So you can write code that works against, say, for example, I don't know, the PSA model or the upcoming network interface card model, which I don't have any good examples of because they're still kind of working on that in Google Docs. That's not very public, so to speak. But these are the things you can do with P4 today. Even if they're not programmable, you have a model of how both the underlying hardware and how your data plane should behave. Okay, this is the question I always get. But why? Well, we have as an industry found a lot of value in representing as much as we can in code. And for some of us, that's as straightforward and as simple as, yes, instead of it being in a bunch of different flat text files or in a million different Excel worksheets in a million different Samba shares, we can now use YAML and check it into one Git repo, and everyone has a somewhat shared source of truth. And that's nice. That is one definition of infrastructure as code. But quite a few have realized that it goes much deeper than that. If we can start defining not just our virtual machines, not just our hypervisors, not just our clusters, but start defining our actual bare metal beyond CPUs, beyond an extra bit of memory or a network port here and there, virtual function on an Intel card there. If we can represent more of our infrastructure as actual code, it unlocks extreme power for a lot of different reasons. A lot of reasons around reliability, a lot of reasons around decoupling. I'll stop myself there from the decoupling. I think we can all agree that with our infrastructure as code, as we have seen outside of the networking space, there's a lot of power there. And that's the point. When we talk about interfaces and atrocious SDKs like the notorious Broadcom SDK, or even the Marvel SDK, Mellanox, any of them, we're given what? A bunch of API calls, maybe some documentation, and a human has to run through, read the documentation, poke and prod these different APIs. Sometimes the documentation lies, sometimes the API lies, and it's just almost this Sisyphean task of kicking water uphill. But what if we had the behavior of both things? We had the behavior of the protocols and the processing we want to do, and the actual hardware that's doing the processing, or virtualized software doing the processing as code. We modeled the behavior as code. We can do that for just about anything. I want to make a point. I want to go back to my point earlier that if it's a packet, you can represent it in P4. Long ago, 5 years ago now, someone took that as a challenge and wrote a paper called dc.p4. And they went ahead and they implemented nearly all of the popular data center, data plane functionality. VXLAN, NVGRE, ERSPAN, et cetera, et cetera. And what they found, even with the original P4, this was written with P4.14, they were able to express all of these things in a minimal amount of code. Now, when we separate our processing code from our description of the underlying hardware that's processing it, we can decouple advancing both our protocols and the underlying hardware from each other. Let's take VXLAN for an example. It wasn't done in the IETF. It came mostly from industry, as far as I'm aware, but it took 4 years to really show up and make a difference. Why? Because they went to the ASICs, the folks tapping out these chips, and said, we want VXLAN. Okay, well, that's going to take us a lot of time. We have to go back and we have to rearrange our parser. We have to rearrange our pipeline. Then we have to make sure that it works. Then we have to tap it out into actual silicon. And so now we have protocol development tied extremely tight to chip development. Now, I think we can all agree that we don't really want Broadcom or even Mellanox or even Intel with their Barefoot acquisition to define how the industry moves forward. If anything, it should be a little bit more top-down, right? Operators should have a little more say, if not directly, if not individually, but in general, as a market participant, should have more say on how protocols are developed and what shows up in the market. And the best way to do that, or to begin doing that, is decoupling this tight coupling of protocol development and hardware development. All right, I'm going to get a little bit into the weeds here to explain more about the why, because once we move past what we can do today with existing stuff, we can start looking beyond to a future that makes, I don't know how I want to call this. It's some forward-looking shit, yeah? I mean, let's be real. No one ever considers their switch to do anything but just switch Ethernet packets, right? We barely trust it enough to do that. Running neural networks or anything beyond that seems a bit space age, if not ludicrous. But here's the thing. We've hit the ceiling of Moore's law, right? The transistors can't get any smaller. We can't really get more clock cycles. And there's only so much die area and heat we can dump on a general CPU. So in order to fight that now, we need to do domain-specific architectures. And I'm not saying anything new here. There's a great presentation that I wish I put a slide up here for, and now I forget the name of it, given about 2 years ago, where they go into this. And they mention Tofino and they mention P4. But in these domain-specific architectures, now we can start doing things that are better suited by these architectures than just generic compute. And a great example here of just how powerful a domain-specific architecture like a line rate packet-specific processor, in this case the Tofino, but there are many more coming, can do things like neural networks. Admittedly basic neural networks, but neural networks nonetheless. In the network, offloading your CPU, offloading your GPU. Of course, we have TPUs and things like that. But again, an example of the power of this abstraction. Something that would be even closer to actual usefulness, complex event processing, right? Wouldn't it be great to take stuff right in the network, removing those round trip times, removing that latency, and actually processing events in the network before it gets passed off to whatever your message bus is? This is something we can do now. The one I'm most excited about is in-network coordination and consensus. With a programmable plane, with this infrastructure or your forwarding plane as code, I can now do something that, from what I've read, and in my own experience, can eat up nearly a quarter of generic compute on a busy cluster, is key value stores and consensus. If you're familiar with Kubernetes, you know etcd. And if you know how etcd runs in the background, it has a gossip protocol for its consensus. It has a gossip protocol for transferring the key value stores. And then it has a consensus protocol called Raft in order to make sure that, everyone's got the same values and everyone's working off the same data. Now, right now, etcd is a Go collection of Go binaries that run on a generic computer, on a generic CPU. Well, storing keys and key values, admittedly small ones, not arbitrarily sized ones, but let's assume for a second that our key values are small enough, not too big, maybe the size of an IPv6 address, or maybe a little bit larger, let's say. We can put those key values in the network, and then we can run a consensus protocol amongst our switches, amongst our network devices. This gives us two things: incredible scalability on the number of key values we can add, change, delete, move, right? And it's below round trip time coordination because there is no round trip time. Your hosts, your pods, your Kubernetes part that's interacting with the control plane is actually getting most of its control plane data from your network's forwarding plane. I don't know. I think that's pretty neat. I think that hasn't been explored enough. And I think that should get some people interested in what this is going to look like in the coming years. Now, here's one that's more close to the RFC 1925 disclaimer I skipped at the beginning because I knew I was going to go off on the weeds. But generally, my presentations are compliant to, I think it's RFC 1925 number 4. Some things are only best understood by those who have built and operated. And here's one that's a little more applicable probably to the audience here today, right now, today. In situ, in-band network telemetry. There was a joke I made in my RIPE talk about proof of transit, which is not a blockchain thing. But imagine, if you will, trace route on some serious steroids, a really, really bulked up trace route. And what I get is not just the path that my packet took, and maybe not just an attestation from each stop or each queue that my flow or my packet took along that path, but I can get real-time data of each queue and each device and each interface collected along the way from point A to point B. Now, yes, that means your MTU might need to be a little bit larger than 1500, but assuming that you're not running 900 MT or 9000 MTU frames, you can stack on quite a bit on top and start adding metadata, collecting that metadata at interesting collection points, and now you have low-level telemetry that you cannot get from SNMP, you cannot get from screen scraping in a very tight loop, and in a lot of cases, you're just beginning to, if you're lucky and your vendor's nice and it works, streaming telemetry. All right. I'm going to stop there because I would like to open it up to a different discussion with folks here with some questions. And yeah, just start a discussion here. Yeah, that's it. That's what I got.